Welcome back to ECE 320A. We're in Unit 11, which is the Active Filter Design Unit. And in this particular video, we want to develop a strategy for frequency scaling transfer functions. If somebody gives you a transfer function, then we might need to know, okay, what's the frequency of interest that we want to scale, and maybe we have a transfer function that nominally has a bandwidth of 1 radian per second. Can we scale that to 100 radians per second with the transfer function, not adjusting or worrying about parameter values, R's, C's, etc. But before we do that, let's look at two different pieces of analysis. One, let's show why a transfer function given by 1 over s plus 1, a first order transfer function, has a magnitude of minus 3 dB at the cutoff frequency. And let's also show why the cutoff frequency, you might sometimes hear people referring to that as the half power frequency. Why are those the same? So let's now look at those before we return to our main goal for this video, which is to develop a strategy for scaling transfer functions. Let's examine then this first statement or topic, which is what's the minus 3 dB point, and is that at the cutoff frequency? Here we have a first order normalized. Normalized means we're looking at a bandwidth or a pole at minus 1. We have a normalized filter, that's capital H of S, 1 over S plus 1. It has a DC gain of 1. It has a bandwidth of 1. Let's now see if or what the magnitude in dB is for this transfer function at the cutoff frequency, which is omega sub c or omega sub n equal to 1. So the magnitude at cutoff for this normalized transfer function, normalized meaning omega sub n is 1 radian per second. Let's now look at h of j omega when omega is equal to 1. That's now the magnitude of h of j1, which now I've written below that. That's the magnitude of the numerator, or actually let me just go ahead and make one more step. We're looking at the magnitude of h of j omega evaluated at omega equal to 1, and h of j omega was just 1 over j omega plus 1. And now we want to find the magnitude of that. Well, the magnitude of this ratio or quotient is just the quotient of the magnitudes. We need to find the magnitude of the numerator, and that's a complex number. In this case, the complex number is purely real, so that should be easy to find. That magnitude is just 1. Then we need to find the magnitude of this complex number that has a real component of 1 and an imaginary component of 1. And that now we can find by taking the square root of the real part squared plus the imaginary component squared. 1 squared is 1 plus 1 squared is 1. So now we have 1 over the square root of 2, or 0.707. That's now the magnitude of our normalized low-pass filter at the cutoff frequency. And let's now convert that absolute number, this 0.707 or 1 over the square root of 2, into a dB value. And we can find the dB by taking 20 log of that magnitude. And that's just the magnitude of h of j1. We computed that to be 1 over the square root of 2, and now let's just manipulate the argument of this logarithm. First, 1 over the square root of 2 is the same as the square root of 2 raised to the minus 1 power. And now let's remember our facts relative to logarithms. If we have the exponent in the argument of a log, we can pull that out in front of the log, so the -1 pops out in front, and now I've gone ahead and said, oh, the square root of 2 is like having 2 raised to the 1/2 power. So again, let's now take that exponent inside the argument of the logarithm out in front, and we have -20 times 1/2 log of 2, but half of 20 is 10, so now we have -10 log of 2, and this is why you might like to have this little chart of logs of these integer values. Log of 2 is actually roughly 0.3, and that then says if we scale 0.3 by 10, we get 3, and that's where then this -3 dB at the cutoff comes from. We've now derived that or shown that for this normalized first order transfer function at the cutoff frequency, or at omega equal to 1, since it's normalized, we're actually -3 dB down from maybe our straight line approximations, which are meeting at the break frequency at 0 dB. That's why we're calling that the -3 dB point. What happens, or how do we then connect, or why is it okay for sometimes for individuals to, instead of calling it the cutoff frequency, maybe they call it the half power frequency? Why is that the case? Well, suppose we now have this transfer function or filter, capital H of S, between the input and the output, and power, remember, is not a voltage. It's proportional to the square of the voltage. In DC terms, power is VI, and I could be, by Ohm's law, V over R. So now we have this V squared over R. We know that power is proportional to V squared. If we now square both sides of that expression for V naught, then we have V naught squared is the quantity HV sub I squared. We can square both of those pieces, and now we have H squared in this relationship. And what is H squared, or what is the magnitude of H squared at the cutoff frequency? Well, H of J1 we just computed, that's 1 over the square root of 2 for this normalized filter. Squaring that, we end up with being 1/2. So now the power is from the input to the output going to be 1/2, or related by 1/2. So the output power is 1/2 the input power at this cutoff frequency. And that's where this half power frequency relationship to the cutoff frequency, that's how you can make those two connected or actually be the same frequency. Now let's go back to our original goal, which was to develop a strategy for frequency scaling transfer functions. Now that we've investigated the -3 dB magnitude at cutoff, and that the half power frequency can be the same as the cutoff frequency. Suppose we want our transfer function to have a different bandwidth. How do we scale the transfer function, or frequency scale? Here's a normalized transfer function, capital H of S, 1 over S plus 1. It's normalized because it has a bandwidth of 1 radian per second. Suppose we want a transfer function that has a bandwidth of 5 radians per second. Well, the S new is now 5 radians per second, and what's the S old? Well, that's just consistent with having a pole at -1. This is now the S old is now 1 radian per second. And we already know the relationship between, or what we can do if we want to perform frequency scaling. We have the new is equal to the old scaled by the frequency scaling factor K sub F. Or if we solve that for S old, which in our normalized transfer function, that's the S that we really have, then that becomes S new over this scaling factor K sub F. And that's now our strategy. Our strategy is if we're given a transfer function and we need to frequency scale that transfer function, then we first find our frequency scaling factor K sub F, and then use this relationship, this ratio of S over K sub F, to replace every S in our original or initial transfer function with S over K sub F to frequency scale the transfer function. In our particular case, then, the scaled transfer function, capital H sub S of S, where the sub S is standing for scaled, is going to be determined or found by, in the normalized transfer function, simply replacing S with S over K sub F. If we do that with our original transfer function, we had 1 over S plus 1, but now we're replacing S with S over K sub F. But our K sub F we found to be 5 if we wanted a bandwidth of 5, and now we can multiply by 1, which is 5 over 5, and we end up with a scaled transfer function that's been frequency scaled to have a bandwidth of 5 is in fact 5 over S plus 5. In that frequency scaling of the transfer function, do we change the DC gain? No. If we set S equal to 0, we still have a DC gain of 1. And so now we have a passband magnitude of 0 dB. We then come out here to our break, omega sub b, which in this case is 5, and then we roll off, and we roll off at minus 20 dB per decade, since we have a first order low pass filter. Where our bandwidth now is 5, and we roll off into the stop band. And that's now how we can frequency scale a normalized transfer function. We simply have to identify the frequency scaling factor, and then everywhere we had an S in our initial transfer function, we replace it with this scaled S expression, S over K sub F. And that's how we would then frequency scale a generic transfer function.